what to build on, what makes them different. And so I think probably the first thing you've probably heard of is optimistic versus ZK rollups, right? So I think the thing to note specifically, again, we talk about data availability. When we post that data back to Ethereum, how do we prove it's true, right? So there are two approaches. Optimistic rollups came first. What they do is optimistically assume that data is valid. So they implement something called fraud proofs. What this means actually is when we do something called withdrawals, so withdrawals being bringing like ETH from the L2 back to the L1, they have to implement something called a challenge period. So a challenge period is 7 days, basically where it's locked up and gives the community to opportunity to essentially dispute the transaction. And so what that looks like is to say, hey, I want to dispute that within the 7 days, and then we will submit a fraud proof, validate that fraud proof, and then if it's good, then we're good to go. For bad, then oh no, you know. The downsides of this, right, is a few things, right? It requires at least one honest node. So obviously there has to be a good person, I guess, going through and doing the fraud proofs. The other thing is this needs to post all the transaction data back to the L1, right? Because what it needs to do is like recreate the history of everything going on. So that is something I will touch upon when we talk about ZK rollups, right? So ZK rollups was kind of the next phase of rollup architecture. This is when we think about, okay, rather than optimistically assume, let's actually submit something called a validity proof upon submission of that data back to Ethereum. And so what this does is allows us to like create mathematical guarantees around validity, creating safer trust assumptions, security guarantees, as well as when I talked about finality before with the challenge period, you don't have to do that, right? You can submit it and then it's verified immediately. I think there are a few things I want to note here that I get a lot of misconceptions about. ZK, which we'll dive into a little bit later, right, is very popularly known as something we use in privacy. With regards to rollup specifically, depending on the ZK rollup, privacy is not necessarily guaranteed. So the use case of ZK proofs in this situation is posting that proof back to Ethereum is expensive, right? Every time we interact with Ethereum, that is expensive. So we want to bring the smallest type of proof back. And it just so happens because ZK proofs have the property of not having all of the information revealed as part of that, is kind of the most, what do you call it, smallest proof. That's not correct English grammar, but you get me, right? To be put back. So the last thing about that too, right, is like we only need to post like transition state data back to the L1 rather than everything as compared to optimistic rollups. So some examples you might know, I put up logos, Scroll, ZK Sync, you might know, what's it called, Linea, Polygon ZK EVM, lots of interesting players in the space. Let's go a step deeper. Okay, we've covered the optimistic rollups. We've covered the ZK rollups. But let's actually differentiate within the ZK rollup itself, right? How do we start thinking in that design space? So the first thing I need to talk about is the ZK EVM. So essentially what you can think of a ZK EVM as is like a magical computer that allows us to execute EVM code, so you can write Solidity smart contracts, but also allows us to kind of translate that into something that is provable, right? Because ZK proofs are math, and how do you turn code into math? I'm not entirely sure. Ask our researchers and engineers, but that's what a ZK EVM essentially allows you to do. This is incredibly difficult to do just based on how the EVM was built, which has given rise to 4 different types of ZK EVMs. So this is kind of where we start talking about, okay, how did the ZK rollups differentiate themselves from each other? So at a high level, type 4 is going to be something that we call high language level equivalent, but not bytecode equivalent. So an example would be like a Starknet or a ZK Sync. What this means for developers specifically is you can write in Solidity, but your tools will have to change to an extent, right? Because it's not to kind of understand the information. Type 3, I'm going to gloss over as sort of the transitionary period to type 2, which is kind of the next stage. I put a frog there because I like this one. But anyways, this is a high-level language equivalent, so the same thing. You can write in Solidity, you can write in Viper, etc. But it is a bug in Viper that caused a hack, right? And the problem was not in the Viper code itself, but actually in the compiler, right? So if you map that same paradigm to ZK EVMs, right, you can kind of audit all of the smart contract code, but there's a lot stronger, at least in my opinion, of a security guarantee when at the lower level, you don't have that overhead of thinking how it's different as well. So that's type 2. Type 1 is kind of fully Ethereum equivalent. So again, like I said, high-level language equivalent, Ethereum equivalent, meaning you can write in Solidity, tools don't change, and there's some little tweaks about like data and hashing that makes it the same. But anyways, the point of like also why you would choose different ZK EVMs is basically, like I said in the beginning, ZK EVMs are really hard to build, right? So something like a Starknet and ZK Sync took the stance of like, EVM's not perfect. Let's actually change it a little bit in order to get certain advantages, like maybe it's faster, maybe we have native account abstraction built in, versus maybe protocols more like Scroll or Linea, where we talk about, no, we want to maintain faithfulness to the EVM because that's where the community is. It just smooths the developer experience, things like that. Everyone's super cracked and super smart, so I'm not going to say one is better than the other, but I think something to think about as devs when you're comparing the landscape. Other things to think about, because we love numbers when we talk about rollups, is the different stages. So stages was something that was defined by L2Beat. If you guys aren't familiar, L2Beat is a really great resource to look up, like, rollup information that tells you about like different security guarantees, like their activity and stuff like that. They define 3 different stages of rollups. So again, when you're thinking about the layer 2 landscape, there's different what we call training wheels that we have as the technology progresses over time, right? So stage 0 is where I would say most of the rollups operate right now. The most important thing to think about there is pretty much like the operators are centralized. So operators being like sequencers. You might hear that phrase a lot, centralized sequencer, right? The source code is available for you to reconstruct state. Stage 1 is kind of the next step, right? How do we let go of those training wheels a little bit more? So then that's when we bring in smart contract governance. This is when we introduce something called a security council, right? So security council is like a group of people who are going to basically arbitrate whether or not an upgrade might be made, things like that. There are specific requirements about like some of the security council people should be on the team itself and some should be external as well, right? And stage 2 is like, woohoo, no, we're completely training wheels off. It's fully managed by smart contracts. Proof system is permissionless. Security council is only there to basically handle like upgrades, not upgrades, soundness errors. So if there's a bug, like creating an avenue to basically say, okay, are we going to upgrade this, making sure we have a good amount of time for users to exit if they don't want to be part of that upgrade. But also another kind of design space to think about when you're looking at the L2 landscape. And so to kind of summarize everything that we've talked about, there's a lot of trade-offs that fit everywhere here. At the highest level I wrote, by highest level I mean it's the first bullet point, finality is what I was talking about. So when you think about challenge periods in optimistic versus ZK rollups, that might be something you think about when it comes to liquidity fragmentation, stuff like that. I'm going to anticipate a question in case somebody might ask, like, oh, wait, when I withdraw from like an optimism to Ethereum, it feels instant. I don't understand. Where's that challenge period coming in? So just to address that point specifically, you might think about bridges, like third-party bridges, basically having separate liquidity pools to allow you to give that feeling. As we all know, bridges are the most like hacked space in the kind of ecosystem right now. But, I mean, there's a lot of strong guarantees that are happening that I'm not a bridge builder, so ask somebody else about it. But anyways, last piece, second piece, right? Like I said again, security guarantees and trust assumptions. So whether or not you're optimistically like waiting for a fraud proof versus saying I'm going to submit a proof on submission. Yeah, validity proofs. And to that extent, thinking about throughput, cost, again, there's a lot of different implementations that have trade-offs. Maybe if you're building a game, you might want something that is faster and cheaper with fewer security guarantees than a different type of app. Developer experience, so this is a trade-off when I was talking specifically about the different types of ZK EVMs and what you're willing to kind of, appetize. What you have appetite for. Decentralization, open source software community. So this is kind of when you get into the ecosystem side of things. So how much do you care about those parameters? And like I said, again, network effects. So that not only affects like how connected are you to Ethereum, for example, but in your ecosystem itself, if you are a builder, what other builders can you interact with, like kind of additive things. So that is rollups at a very high level. I'm going to scare you guys a bit. Rollups are not the end game. They can still be very expensive. Why? So like I said, oh, I heard some chuckles. Let's look at this again. But anyways, let's dive into maybe something that is a bit more of a current event, right? So like I said, when I talked about data availability, that's putting data back on Ethereum. But what do we remember about Ethereum? Every time you interact with it, it is very expensive. So how do we get around that, right? So this is something called EIP 4844, which was introduced, I think, sometime this year, which essentially created something called blobs, right? So blobs are a separate type of data structure than what was traditionally known as call data. So before, you would post information to something called call data, and call data is permanent and there forever, right? The thing about rollup data, right, is you're really only posting it there for like verification. So it doesn't need to be there forever, right? So blobs are actually an ephemeral type of data storage. It will like go away, I think, after 18 days. I'm not the most current on that exact number. But essentially what that does is allow us to use a different type of space. The other thing that is really cool about this as well is it is a separate fee market. So when it comes to competing for, like, I guess, data on Ethereum, blobs are a completely separate space. So what that looks like or means for rollups is you are not as exposed to the fluctuations in the market on Ethereum versus in call data versus blob space. So I guess the result is this is actually still not the most perfect solution. That's when you might start hearing things about like sharding, dank sharding, things in the future of the Ethereum protocol, but just think of this as, again, a high-level primer on what you can expect for the rest of DevCon. So other things that I just want to kind of say to put words in your head is there are, other scaling solutions that have kind of produced or been created. So you might hear something called a validium. So a validium is basically a chain that does like off-chain computation, proves via validity proofs, but they use off-chain DA. So another kind of buzzword to think about is now we're talking about data availability layers. I don't work for these companies, so I can't go too deep into them, but if you want to investigate EigenDA, Celestia, Avail are kind of the new design space you might think of there. And Optimium, I forgot an I, is basically optimistic rollup plus off-chain DA. And then the last one is going to be called a volition. So a volition is essentially the marriage of a validium and a ZK rollup, where you can kind of switch between whether or not you want to do on-chain DA versus off-chain. If you're looking for specific examples, again, head to l2beat.com. It'll actually list a bunch of different projects in the space and also what they are. Okay, cool. I don't know how much time I have left. I figured I would be talking for a long time. So, okay, my backpack is back there. I have swag for somebody who shouts out the answer here. Okay, which type of ZK EVM is bytecode compatible? ABCD. Okay, those are all numbers and not letters. I don't know. The answer is H. Everyone is right. Or not everyone is right, I guess. But, okay, this didn't work out as well as I thought. I did not think there would be this many people here. But thank you for participating. Okay, let's move on. Let's talk about zero knowledge. Okay, so this is some knowledge about zero knowledge. Basically, at a high level, right, zero knowledge proofs allow for a prover, so a person to prove to another person, the verifier, that they know something without revealing the information itself. Right? So what does that mean specifically? So when it comes to ZK proofs, there are three main properties. We think about completeness of the proof. So that means if the prover knows the information, they can convince the verifier with their proof. Soundness means if the prover doesn't know the information, they can't trick the verifier. And then zero knowledge is, like, I guess, pretty self-explanatory. The prover doesn't have to reveal any of the actual information itself. So there are two types of ZK proofs that we're going to get into, something called interactive proofs. So this is a type of proof that requires back and forth between the verifier. An example that is pretty common, you can just Google ELI5 interactive proofs, and this is a picture you get from Chainlink. Essentially what it is this example says, okay, I have Bob and Alice, and there is a magic door in a cave. And the magic door has a magic code that Alice knows, but Bob does not. So Alice wants to prove to Bob, hey, I know this code, but she doesn't want to tell him he knows this code. right? So the process basically looks like you have path A and path B into a magic door that Bob can't see. And so Alice will randomly choose a path, and then Bob will say, come back from path B, and then she'll come back from path B. And he's like, come back from path A, and she'll come back from path A. So what you can think of this as, if he asks her enough times and she can consistently come back in whatever direction that he wants her to come, that means she was able to cross that magic door, and therefore she also knows what the secret code is. So that's interactive proofs. When we talk about non-interactive proofs, that's basically saying the prover can say, hey, I'm going to give you one proof or like one piece of information, and the verifier says that's all I need to know. We don't need to interact past that, right? So the example here is about proving that I have completed a Sudoku puzzle. This is a little bit more complicated, so I'm going to dive into it deeper, but this is going to be what we think about when we talk about ZK Rollup space, snarks, validity proofs, etc., right? So the way this works is actually something called hashing. So hashing is a one-way transformation of data. So that means like if I say, oh, I did 1, 2, 3, 4, 5, 6, 7, 8, 9, I can hash it and give you some like long string of letters and you won't know the actual letter. But what you do is you basically hash each cell's number in the Sudoku puzzle. You combine all of those hashes in commitments for rows, columns, grids. I guess I'm just assuming everyone knows how Sudoku is played, but maybe you don't. So I'll step back again and also explain how Sudoku is played, in case you don't know, because we're all about starting from the top. Essentially, Sudoku is this grid, and what you need to do is be able to count 1 through 9 from the top to bottom, 1 through 9 across the rows, and 1 through 9 in each box, and there's no duplicates. Okay, cool. We all know what Sudoku is. If you can't get anything away from this talk, I hope you remember that specific piece. But essentially what you can do is create all these like commitments of the different forms of all the ways you created a Sudoku puzzle. And essentially the verifier is able to use cryptographic algorithms to understand, hey, yes, everything you sent me is, every row you sent me fulfills the requirement, every column you sent me fulfills the requirement, et cetera, but I don't actually know what the solution is, right? So that's how a non-interactive proof works. So now let's actually talk about snarks versus starks. So maybe this is also something you've kind of heard and been like, huh, what? Okay. So we'll dive into it, right? So snarks are succinct, non-interactive arguments of knowledge. So these are ZK proofs that are succinct, so they're small in size. They're non-interactive, so that means they don't interact with each other like the prover and verifier. These are very compact proofs that allow for fast verification. Thing to note is they do require a trusted setup. So a trusted setup is a pre-processing phase that allows basically creators to create a public and secret key for, like, I guess, the actual proving. The secret key needs to be thrown away, so this is kind of, I guess, a con of ZK snarks, which we can talk about a little bit later in the next slide. How do we solve for this? So again, another acronym that I heard, and I was like, what is this? And I'll just explain it very quickly. If you heard MPC, you might hear it later. This is called multi-party computation. This is allowing basically a more secure way of generating those keys, right? So rather than just like a single instance of like public key, private key, MPC essentially allows every participant to have a part of a private key and then work together without revealing their part of the private key to create the full one, right? So, I mean, there are trade-offs again, right? This doesn't scale really well when you have a lot of parties. It is vulnerable to collusion if like there's, I guess, non-good participants. But I'll give another example. So imagine all these frogs are pirates. And imagine all the pirates are looking for the secret treasure map. So they want to complete the treasure, but they don't want to show each other what piece of the map they have. So what they actually do is they divide each of their pieces into a bunch of smaller pieces and give everybody one part of their smaller piece. So no one knows your complete picture of what your piece is, but at the end of the day, everyone does have every piece necessary to create the full map. So that's NPC in a nutshell, with frogs and pirates. Okay, moving on. Let's forget everything. Actually, don't forget everything, but now we're going to talk about starks. So starks stand for Scalable Transparent Argument of Knowledge. So this is transparent because you don't require a trusted setup. It's also non-interactive. This is really good for handling very large, complex computations. However, the problem with them is they have larger proof sizes as compared to snarks. And so this is where we thread again through data availability, right? The size of that proof is very important for when we post it back to the L1, because if it's bigger, it's more expensive, right? So, I mean, again, these are different kind of ways that rollups have for move forward. So like a Starkware handles ZK Starks. However, not all is lost. Another interesting design space that I'm just telling you about that I learned, right, is I guess math is cool because you can put math on top of math. And so what that looks like in some solutions is you have a Stark, which is very good for computing large, complex computations. And then you wrap it, you prove that it was true in a Snark, which is really good for making it smaller. So an interesting thing to think about. But anyways, at a glance, you can kind of see snarks have a trusted setups. Starks doesn't. I put this here. Post-quantum means quantum resistant. Basically, snarks right now, quantum computers aren't there yet, so please sleep soundly. But in the case that quantum computing gets there, snarks aren't necessarily quantum resistant. Starks will be. Like I said, when it comes to developer tooling, starks are less, I guess, adopted, so there might be less information in the space. When we talk about, I guess, a ZK or a Starkware, for example, they'd use Starks, they have to use a different VM, they have to use different, I guess they write in Cairo, for example. So super smart team. It is a little bit different if you're like a Solidity dev moving in. And then I'm going to move forward. Hello. Yes. No. So post-quantum, I should have used like the layman's term. So post-quantum means possibly quantum resistant. So what that means is quantum computers are not at a stage that they can hack stuff yet, or hack snarks, right? But, you know, maybe we get into a world where that is. The way snarks are created is something called elliptic curve cryptography. I'm not going to explain it because I'm going to butcher it, but Starks use like random hashing, and basically hashing is going to be quantum resistant, but elliptic curve cryptography, whoa, that's a mouthful, is not. But we're not at the stage yet where we're thinking about it, but yeah, cool. Good to know. I will not write post-quantum anymore because it is confusing. Thank you for that. In the front. Okay, another quiz time. I put stretch sesh because I also expected people would stand up and be like, I'm tired, but I guess no one's tired. Oh, nice, thank you. Okay, what does SNARK stand for? Oh, perfect. Okay, I don't have enough swag for everyone who answered, but if you find me first, you will get a magnet. Okay, moving on. We have 30 minutes left, so hopefully we can get through everything. This is where we just get into current events, things I see on Twitter that people argue about that probably don't really matter in real life, but whatever, we're here talking about it. So let's talk about rollups, right? I went over optimistic rollups, I went over ZK rollups, but did you know people define more types of rollups? Let me list all of them for you that I saw on Twitter recently. Sovereign, enshrined, based, modular. Yes. Okay, cool. So let's actually just go through kind of, I have like a slide per each. We're going to define it, and then you can find people who work at those protocols to explain it to you further. But before we start off, we have to start from just kind of the base idea of modular blockchains, right? So modular versus monolithic. Monolithic blockchains do everything. They do consensus, they do settlement, they do DA, and they do execution, right? So something like a Solana would be a monolithic blockchain. Technically, Ethereum was a monolithic blockchain until the rollup architecture was introduced, right? So modular blockchains do a subset of that. So they might only do execution, they might only do data availability, they might do a subset and multiple. And so that's kind of when we get into all these new definitions of sovereign, based, enshrined. I said something else, I don't remember, but we'll get into it. Okay, cool. So now we start with the basics again, right? So what I talked about before, you know, rollups you might know today, Optimism, Scroll, Starknet ZK Sync, Linea, Polygon ZK EVM. I'm sorry if I didn't name you and you work on that protocol. I respect you. I just don't remember you right now. But essentially what those are going to be what we call now smart contract rollups, right? So those are controlled by smart contracts stored on the L1. What they do is, again, again, like I said before, store rollup state, track deposits, withdrawals, handle verification. Key takeaway here is they mainly handle the execution part of it. The other key takeaway here is something we're going to get into when we talk about enshrined rollups. So enshrined rollups are different from smart contract rollups in the sense that they integrate with the L1 at the consensus level. So that means something has happened at Ethereum core that they are now interacting with. What that means specifically is when we talk about smart contract rollups, right, we have an external party determining what that smart contract looks like, right? We need security councils, multi-sigs. You need a bridge for L2 upgrades So when we talk about enshrined rollups, you don't need all of that, right? Because it's enshrined within Ethereum itself. For a ZK EVM enshrined rollup, like validators don't have to re-execute everything because everything's enshrined in Ethereum. The cons here are going to be VM inflexibility, right? So in this case, you're married to whatever the L1 VM is. The cool thing that I will talk about at the end of this presentation is about all the new different types of VMs that are coming about that's helping with scaling, right? So you lose that. The other part is like it's slower to upgrade. You don't move as fast in terms of like development. It might be more complex. But there are pros and cons, like I said, and there is a space where actually both of them live together. So we're all a happy family. Cool, moving on. Oh, I put a logo here. This is Tezos. So Tezos is an L1 blockchain, if you don't know them. They are doing enshrined rollups in some capacity. I don't know how, but find a Tezos person and they will tell you. That's my tip for DevCon week. The other piece you might have heard of is based rollups. So based rollups is, I guess, not the traditional term of like you find in Urban Dictionary, but this is, I guess, the nerd sniping term for people who are interested in Tycho, right? So based rollups basically use the L1 for sequencing. So if you remember when I talked before about operators, right? Operators are a centralized sequencer that kind of take everything together. Base rollups basically use Ethereum for sequencing. So what this allows us to do is inherit the decentralization of Ethereum and inherits the liveness of the L1. So if Ethereum goes down, the sequencer goes down, like we were FUCKED anyway, versus like a centralized sequencer going down. That's a different case, right? And it is simpler when it comes to like decentralization of the sequencer. The con part of it, right, is if you want to get into it, we can talk about it after. I'm not going to go over it here. But there are different performance improvements that rollups do by like fixing the way they sequence stuff that you obviously won't get in this case. And the other part, maybe a good thing or a bad thing, depending on who you are. MEV that happens is going to be taken at the L1 level. You no longer get like the sequencer MEV from L2s, right? Because L1s are handling sequencing. The last piece we're going to talk about here is sovereign rollups. So sovereign rollups are kind of like I choose everything myself because I am sovereign. So what that means is I choose my own execution. I choose my own settlement layers. The pros here basically are, again, talking about like that forced upgrade from smart contract rollups, right? So smart contract rollup upgrades, if you want to participate in the L1, or if you don't want to participate in the L2, you just have to exit, right? Because the smart contract is upgraded. Sovereign rollups are actually like, hey, we're going to choose our own settlement. We're going to choose our own execution. We're going to do everything our same. It's what you can think of as the nodes control how they interact with each other. So what that looks like is in order to upgrade a sovereign rollup, you have to actually fork like a traditional L1. And so that allows us to basically kind of maintain whatever state we had before if you don't want to participate in the upgrade. The interesting thing here is, right, like this is a design space where we might be using Ethereum or Bitcoin as purely data availability and then not care about like consensus, settlement, etc. Maybe with somebody else, right? I didn't put a logo here, but if you want to read more about it, Celestia is a project that is working a lot on sovereign rollups. But yeah, so section 4 is like other niche topics that aren't handled by rollups. I don't know how much time I left, but I think I have. Yes. This is what I read online. So the answer is yes, as far as Google and an article that I read is correct. Cool. So let's dive into other hot topic. So something you might have heard of recently is trusted execution environments. So trusted execution environments is when we start talking about hardware with regards to privacy and scaling, right? So a TEE is essentially an area within a computer's processor where you can run code, but nobody else can access it. So like the OS actually can't even access that space, right? What this means, it is isolated. So it creates something called a secure enclave, is something you might have heard of, within the main processor. Only pre-authorized code can run here. It has something, not every TEE has this, but some of them do. They have attestations, right? So TEEs that you might use can produce an attestation to prove to others that the code is running is genuine and unmodified. Sorry, I just burped. And the last piece is confidentiality. Like I said, because this is a separate part of the, I guess, the hardware, you get to do stuff that's encrypted and inaccessible to the rest of the system. So something that's really important maybe for like privacy solutions in that new space, right? When we think about it further, actual TEE providers you might have heard of or now know, because I am saying it right now, Intel SGX is something, it's going to be a hardware provider. AWS Nitro is a TE provider, but they're more of a virtual machine. And like I said before, this supports use cases like privacy. It actually protects against MEV, which is a really interesting space. Flashbots is doing stuff in that direction. If you want to Google Flashbots, TEE, MEV, that would be a good place to start. There's a question. Sorry, what? Oh, yes, yes. There's ARM and Trusso, and I didn't list all of them. There's a few, but I only put 2. I should have put all of them. Thank you for that. But moving on, why we care about TEEs, right? It's a hardware secure environment. But to that point too, it is going to be vulnerable to whatever hardware specific attacks there are. You are putting trust in a different party, such as an Intel, such as an AWS, which comes with its own trade-offs. But these are very battle-tested, widely used projects. It allows for fast computation with hardware acceleration. I think the con side is when we talk about like participating in networks, if you require a TEE in order to run, i.e. specialized hardware, it might prevent certain people from participating in the network. And then integrity guarantees, they have attestations, but again, like I said, it does require trust in the hardware manufacturers. So whatever you have appetite for. But actually, this is something interesting I want to dive into when we talk about a particular use case of TEEs when it comes to rollups, so the L2 design space, right? And I mentioned before something called multi-provers. So this is a new buzzword that you should keep in your mind. So essentially, if we look at systems today, we have basically a single proof system. So if there's a bug in that proof system, that's a vulnerability, right? So now there's a new thing that Scroll has done. I believe Tycho has as well. If somebody else is doing, please let me know, called multi-proofers. And what this essentially says is we want multiple proof implementations to basically reach a consensus of truth in order to like strengthen the security guarantee, right? There's different ways to do multiple proofs, right? We have fraud proofs, but that will introduce, I guess you could say, the challenge period, so you have the problem of finality running in again. Another way is just to build a second ZK EVM because you're crazy. So do it if you want. I don't recommend it. Or maybe recommend it, I don't know. And the third piece that Scroll at least is moving forward with is doing a separate TEE, right? So we're doing the transaction in a TEE as well, generating proofs there. And the way we're actually doing it, again, when we think about having multiple implementations, we are doing via different types of hardware. So if you see Intel, SGX, AMD, AWS, things like that, I guess another cool thing to think about when you're considering the rollup space. What else do I have? Yes, okay, this is the last piece. And I have 50 minutes left. Wow, I talked for so long, for so short of a time. Sorry. Our ZK EVM's endgame. So this is probably the spiciest thing, right? Because I think you've probably been hearing a lot of rhetoric about like ZK EVMs, fast finality, like we want to be, I guess, on par with the latest developments in Ethereum. But there's something that's really interesting in terms of the ZK VM space. So ZK VM, you can kind of think of, it's relatively straightforward. You just take the Ethereum out of it. It basically enables, like I said before, computation that is provable, but this time it's more general computation, right? So you're not limited to whatever the EVM does. It's designed to support a broad range of applications. The cool thing about ZK VMs that it has allowed developers to do is actually build circuits in languages that are more mature. Right, so if you're building circuits right now, you might build in something called Circum, right? When we talk about ZK EVMs that are being built right now, we're writing custom circuits, which requires custom security auditing, which requires, like, I guess, a very specific skill set. But with ZK VMs, what it allows you to do is actually do that same thing, but do it in Rust, right? You have a bigger pool of developers. Rust has its own, like, really cool, like, speedy things that it does. And I guess projects to look out for that are doing ZK VMs is Risk0 and Succinct. And this is really cool, actually, like I mentioned before, of what this allows us to do, is actually Succinct built something that allows optimistic rollups to start implementing validity proofs. Right? It's very, very new, but this is kind of the new space that ZK VMs introduce, right? The other thing, and like what that allows us to do, right, is accelerate ZK development in general. So when we think about blockers to privacy use cases, identity, et cetera, it's all like, you need a lot of, I guess, background information. But now you can do it stuff like Rust. And like I said before, the auditing surface is easier. And so I guess new things to look up, research, Zeth and SP1. ZK VMs are an interesting design space to follow. Okay, so these are my sources that I kind of was like looking through. If you want all of this information or want to read more, I had a pretty wordy slide because I feel like this is more useful as a reference. But this is a QR code to my Beacons page, which has a link to the slides themselves, so feel free to save it. If you want to follow me on Twitter, feel free. I mostly post about frogs, so I guess follow at your own peril. Yeah, I think I have 47 minutes left, so I kind of screwed myself over with 47 minutes of Q&A. But that's everything. I think that QR code is supposed to allow you to ask questions over chat, but I'm also happy to just, no questions. Yes! Oh. No! Do I write about real frogs? No, I only post frog memes, but I'll tell you about my favorite real frog, because I have 47 minutes to talk about my favorite real frog. And my favorite real frog is the desert rain frog, which I have in a slide. Yeah, cool. This is my favorite frog. And the cool thing about this is it never becomes a tadpole because it lives in the desert. It just immediately becomes a little frog. The end. Okay, cool.